different scientists are suggesting different ideas in a different time period. So using that, we study the structure of the atom and the nucleus. So what is inside the nucleus? Now we are going to see that what is inside the nucleus. Composition of nucleus. So composition of nucleus, it contains the proton and neutron. So in atom, electron, proton, and neutron are inside the atom. Inside the nucleus, it has the proton and the neutron. The number of proton in that nucleus is called atomic number. That is what the word letter Z. The total number of neutron and proton in the nucleus is called mass number, and that is A. That is what the letter A. Then mass of the proton is nearly nearly 1,836 times of electron. So it's very great number compared to the electron. Then the mass of the proton is 1.6726 × 10^27. That neutron mass is nearly equal to the proton mass, slightly greater than the neutron mass. So that is equal to 1.749 into 10 to the power minus 12 sample of that. So usually we are given the letter that element is in X. That mass number is titled in the superscript, and subscript to that is the atomic number. Okay. Then that nitrogen 15. So nitrogen 15 means 15 is the mass number, 7 is the atomic number. Suppose the 7 is not indicated, we can tell it as nitrogen 15. So since the nucleus is made up of positive charge proton electrically, it is neutral, because the number of protons are equal to the number of electrons. Charge also equal to this in the neutral state. And next thing is isotope, isobar, and isotope. Isotopes is the same element has a different mass number and same atomic number is called isotope. Example for that, the hydrogen atom, protein, deuterium, tritium. That another example for that, carbon 12, carbon 11, 12, 13, and 14. Carbon 12 is approximately, it is 98.9, so it is large amount in nature. Then carbon 13 is 1.1%, but carbon 14 is only 0.0001%. So it's very, very small in the gas molecule. So that carbon 14 is radioactive element is produced due to the cosmic rays or the sun rays. So it is produced from the outer cosmic rays or sun rays. So the ratio of the carbon 14 and 12 is maintained by the natural. That's why it is maintained. Then electronic and structure chemical properties of the elements are same. Isobar, the atom different element having the same mass number is called the isobar. That is the letter is the example of the is that chlorine argon has the same number of 40, but it has the atomic number 17 and 18. So isotope and isobar are chemically different elements. They are different in physical and chemical properties. Isotope is called the different element has the same number of neutrons. So neutrons, that boron 12 and carbon 13 has the same number of neutrons. Atomic and nuclear masses. That atomic masses is equal to 1 atomic mass unit. That is defined by 1 atomic mass unit is defined by 1/12 of the carbon 12th atom. That is equal to 1 unit equal to carbon mass of the carbon 12 atom divided by 12. So you get 1.6602 is 10 to the power minus 27 kilograms. So you know the mass of the electron, proton, and the neutron. So calculated that value, you will get carbon 12 equal to 12 units. Okay. So the mass of the carbon 12 is 12 units. By using the Bain mass spectrometer, it is measured that the radioactive carbon, all the element has the nearly same value. The average of the isotope, that is carbon, radioactive element, and other elements are having the same mass. Next thing is size and density of the nucleus. Size from that Rutherford alpha particle category. The Rutherford calculated the size of an atom is 10 to the power minus 10 meter. The size of the nucleus is 10 to the power minus 15 meter. The result is greater than 10. That is, the radius of the atom is used to find the empirical formula is R equal to R0 to the power of 1/3. Here, mass number of the nucleus at the constant R0 equal to 1.2 Fermi. Then Fermi equal to 190 to the power minus 15 meter. So using that, we can calculate the radius of the nucleus. So mass effect at the binding energy. So mass effect and binding energy. So mass effect and binding energy. So we will consider that mass of the neutron. So this is a neutron, number of neutron into neutron mass, number of proton to proton mass, then electron. So somewhere adding all these values, you will get that 12.095558 unit. But actual mass of an carbon 12 is 11.9997. That mass change difference in mass, that actual mass and the calculated mass is 0.988 units. So it is difference in that mass is called the mass defect or change in mass. So how to calculate the change in mass? Change in mass delta M equal to that mass of the proton Mp into that Z is the atomic number. N is the nuclear into mass of the nucleon is Mn minus F actual mass of the element. So binding energy equal to this mass into c square. This is from the Newton's equation of motion. Energy E equal to mc square. So this is the mass delta M into c square. So this will be the mass. We can give the energy. So here energy is converted into mass. Mass is converted into energy. Here the small amount of mass is converted into energy. That energy is used to combine the nucleons inside the nucleus. So that is called binding energy. Here binding energy equal to Zmp, mass of the proton. So here Me, that is atomic number into mass of the electron is added here and subtracted here. So there is no change in the equation. So next equation Z is common. So we can take it out. So remaining values are here. So mass of the proton plus mass of the electron is mass of the hydrogen atom. So write it here. Then M plus that negative sign is taken out. M plus is that Me there. So this is the actual mass of an atom. So we can write it Ma. So write it here. So binding energy equal to this value into this power. So atomic mass unit equal to mass already we calculated that 1.66 minus 47. So c square 3 into 10 to the power of 8 whole square. So multiply that you will get 14.94 into 10 to the power minus 11. So R that is equal to 931 mega electron volt. So the next thing is energy. Binding energy is defined as the binding energy divided by that mass number gives the binding energy per nucleon. So to remove the one nucleon from the nucleus is called the binding energy. The energy required to remove one nucleon in the nucleus. So it's called the binding energy. B equal to this formula divided by B. So here there is a graph for the binding energy curve. This is called the binding energy curve. Net axis is number of nucleons A and the average binding energy is mega electron volt in the y-axis. Here the lighter elements are here. One helium, hydrogen, then oxygen, further lighter elements are in here. And the most stable element is iron, 56. So it's the most stable element that the binding energy of the iron is 8.8 mega electron volt. So it's the most stable element. And from mass number 40 to 120. So 40 means up to here to 120. From here to here. So 120, it is stable. The average binding energy of it is 8.5 mega electron volt. So all the stable elements are here. Then above that 120, that means that uranium is a unstable element. That binding energy is 7.6 mega electron volt. So it is not stable. It is unstable. It will radiate the energy. It will emit the particles alpha, beta, gamma like that. So it will give the it is not stable. So it will produce the two new element and release the energy. So that's called the nuclear fusion reaction. Here light elements are here. The light elements are combined to form a heavier nuclei. That heavier nuclei is that process is called a nuclear fusion reaction. So that the light elements are not stable. So fused together, we can make a heavier element that is called nucleus. Proton and the neutrons are inside the nucleus. We know that same charges are repel each other. Then proton and protons are inside the nucleus. So two protons have the same charge, that is positive charge. So definitely they will repel each other. But inside the nucleus it is a stable because very strong nuclear force acting between the two protons. That force F is equal to K into Q square by R square. Substituting that you will get the value of 230 Newton force is acting between the two protons. So by using the acceleration A is equal to F by M or F equal to Ma from the formula we derived A equal to F by M. Substitute that value, you will get 1.4 10 to the power of 29. This value is nearly 10 to the power of 28 times greater than the acceleration due to gravity. So it is very stronger compared to the gravitational force. So very strong attractive forces acting inside the nucleus. So the Coulomb's electrostatic force overcome by the strong nuclear forces acting inside the nucleus. So 1913 and 1950, their experiment was carried out. From that, they have concluded that so strong nuclear forces acting between the two protons and the neutrons, then proton and neutron. So here the distance between the two proton and neutron and proton is very small, 10 to the power of minus 15 meter. The nuclear force is a very strongest force. It's acting between only the 10 to the power of minus 15 meter. So this force is an attractive force acting between the proton, neutron, neutron, proton, neutron, neutron. Then the strong nuclear force does not act with the electron because the range is very, very small, so it is not affect